Welcome back to our AI Security edition of the Vulnerability Chaining Masterclass Season 2. Today we are diving into a deceptively simple yet devastating scenario: unbounded consumption leading to resource exhaustion. Imagine a model that's never told to stop. Every extra input drains CPU cycles, chews up memory and network bandwidth, and eventually triggers a chain of events that leaves services down and budgets blown. OWASP highlights this as LLM10 in its top 10 for 2025. In this fourth episode of Season 2, we'll explore how uncontrolled resource use escalates into denial of service and even denial of wallet, causing service outages, financial losses, and system crashes. If you missed episode 3, How Hackers Break AI Guardrails, be sure to queue it up for later. It's a perfect primer on how attackers slip past protections and sets the stage for today's episode. Before we dive into the mechanics, a reminder. This series is for educational and defensive purposes. We're exploring how adversaries abuse AI systems so that you can build safer applications. Always obtain proper authorization, follow responsible disclosure, and use these insights to strengthen, not undermine your systems. You are responsible for how you apply this knowledge. So what exactly is vulnerability chaining? In AI security, it's when attackers combine multiple low-severity weaknesses to produce outsized harm. In practice, resource consumption flaws often form the foundation for catastrophic denial-of-service attacks. But why should you care? Because one leak can trigger a pipeline-wide collapse, silently drain budgets through a denial of wallet, and throttle legitimate users. Today we're dissecting an attack chain with 3 stages: unbounded consumption of inputs, bypassing guardrails like rate limits, and culminating in resource exhaustion. Keep this chain in mind as we dig deeper. Unbounded consumption is when an LLM application allows unlimited inference or resource use. Without strict limits, attackers can degrade service, crash your application, or bankrupt you. They target compute, CPU-GPU cycles, memory, context windows, budgets, token quotas, and I/O network storage. The business impact is dire. Legitimate users experience high latency or timeouts, auto-scaling can lead to runaway cloud bills, and shared API limits get saturated. It's no wonder this risk sits squarely in the OWASP top 10. Attackers have a toolbox of strategies for unbounded consumption. Token flooding maximizes prompt length to drain quotas, while context stuffing fills the model's context window, forcing expensive recomputation. Recursive loops create sub-agents that run indefinitely. Sponge attacks craft inputs that maximize energy consumption without necessarily generating large outputs. Retrieval storms make RAG systems fetch and embed massive documents, and multimodal heavy uploads high-resolution images or large audio files to strain encoders. The strategic insight here is that generating malicious requests is cheap, but processing them is extremely costly, a glaring asymmetry that attackers exploit. Patterns emerge when we study how unbounded consumption destabilizes AI systems. Compute hotspots arise when long context inputs and high temperature settings lead to complex reasoning paths, resulting in GPU memory overflows and latency spikes. Fan-out amplification occurs when an agent's prompt forks tasks, for example, researching dozens of companies, causing exponential growth in backend calls. External amplification stems from unbounded RAG queries or browsing loops that repeatedly fetch massive datasets. Attackers also induce output bloat, coercing the model to produce excessively verbose or junk responses which block threads and delay others. Ultimately, all of this leads to a denial of wallet, where resource costs translate directly to cloud bills and budgets evaporate. When we map these elements into a chain, a sobering picture appears. A small inefficiency in a single prompt can scale catastrophically across multi-agent systems. First comes input flooding, where massive context or recursive triggers are sent. Next is amplification. As agents spawn additional tasks, RAG fetches broad datasets and tools execute fanouts. This leads to exhaustion, CPU spikes, memory overflows, and depleted token quotas. Finally, we reach the impact stage: service denials, latency spikes, and ruinous denial of wallet costs. Keep this chain front of mind because the next slides unpack how attackers operationalize it. To truly appreciate the threat, let's walk through a hypothetical attacker's playbook. They don't need a complicated exploit, just persuasive prompts that make your model think deeply about a recursive paradox. One request can balloon into 50 internal tool calls and 50,000 tokens, an amplification factor of 50,000 times. Their steps are methodical. Recon probes your limits, finding heavy tools, testing context gaps and timeouts, and identifying retrieval systems. Payload crafts a sponge: recursive logic, massive input, variable expansion, and chain triggers. Execute bypasses guards with asynchronous batches, split inputs, and rate limit evasion. Fanout amplifies load through agent forks, multi-tool calls, and retrieval storms. Output maximizes generation with verbose text, infinite loops, and scraping timeouts. exhaust drains the system, spiking CPU, GPU, overflowing RAM, burning budget and causing latency. Finally, persist sustains the DoS with auto retries, low and slow approaches, rotating ITs and orchestration. That's how a simple prompt becomes a service-killing machine. Attackers rarely stop at a single vector. Multi-vector DoS attacks combine several techniques to orchestrate sustained brownouts. One tactic uses orchestrated botnet accounts that look legitimate and send low and slow prompts just below throttle limits. Another is cross-service amplification. A single prompt triggers dozens of downstream API calls. The goal isn't an outright crash, but a sustained brownout, latency spikes and partial failures that evade simple up-down monitors while racking up huge costs and frustrating users. When combined in the triad combo, a sponge input, retrieval storm, and output bloat, the impact is maximized. Recognizing this triad is critical to thwarting complex threats. Let's ground this in a real-world case. A customer support chatbot using RAG accessed a vector database, a web browsing plugin, and boasted a 128K context window. Attackers exploited three tactics: a retrieval storm by asking it to compare 50 competitor websites, context bloat by injecting 80,000 tokens of reference material, and recursive looping by instructing the agent to repeatedly check and regenerate its output. There were no strict timeouts on the browsing tool. Retrieval fetched 50 chunks instead of the top 3, and there was no circuit breaker for runaway costs. As a result, latency increased tenfold, 200 milliseconds to 2 seconds. 45% of requests returned 503 timeouts, and the system burned roughly $4,000 per hour. Within 15 minutes, 90% of legitimate users were effectively logged out. The fix? Implementing a simple request budgeting control. This case underscores that unbounded consumption isn't theoretical, it's happening now. If you think your organization is immune, consider this. Roughly 62% of organizations have no per-user token limits, and around 40% of traffic comes from unmonitored shadow AI routes. That means employees using personal API keys or BYOK tools create a massive visibility gap. Most companies monitor costs monthly, not continuously. A denial of wallet attack can burn a quarter's budget in hours, while billing alerts often take a day to trigger. Operations teams track uptime, but rarely track token velocity per user. So by the time service degrades, the damage is already done. As the slide bluntly states, you cannot manage what you do not meter. The detection lag between a cost anomaly and an alert is dangerous. The takeaway is clear. Instrumentation and granular metering are not optional. Unbounded consumption isn't just a technical problem. It has far-reaching business consequences. Financially, denial of wallet leads to unexpected cloud bills that can exceed $10K overnight and result in SLA penalty payouts. Operationally, resources get staffed, critical services are throttled, and engineering teams are drained by incident response. Brand and legal impacts include eroding availability trust, customer churn due to 503 errors, and contract breaches on uptime guarantees. Strategically, there's an innovation tax. Budgets shift from building features to firefighting infrastructure, slowing adoption of agentic AI. During a sponge attack, the cost multiplier can spike 10 temps to 50 temps relative to normal inference. Brownouts, partial service failures, are more common than total outages, but they are just as damaging. In short, ignoring unbounded consumption threatens the bottom line, operational stability, and customer trust. How do we choke off resource abuse at the edge? Start with input hardening. Enforce hard token limits on incoming prompts and reject payloads exceeding the task's requirements. Normalize and sanitize prompts to strip invisible Unicode characters and excess whitespace used in invisible prompt attacks. Cap recursion depth and the number of tool calls per request to prevent infinite loops. On the output side, establish deterministic caps. Terminate generation once a token limit is hit. Enforce strict response schemas so the model can't waste tokens with verbose yapping. And when limits are hit, degrade gracefully. Fail with a standard 429 or fallback response rather than retrying aggressively. The core defense principle is to enforce limits before and during generation, not just after. The accompanying code snippet illustrates validating prompts and configuring output caps. Simple, effective, and essential. Edge controls are only the first line of defense. You also need architecture-level guardrails. Traffic control involves adaptive rate limiting. Use tier token buckets per tenant and limit not just by request count, but by total tokens processed. Concurrency bulkheads cap parallel requests, so no single user monopolizes your GPUs or vector database connections. Architectural guardrails include RAG constraints. Set strict limits on retrieval depth and document size, and cache frequent queries to bypass expensive inference loops. Implement circuit breakers to fail fast when latency spikes or error rates rise, preventing cascades across microservices. Observability ties everything together. Enforce egress allow lists for web browsing tools, limit download sizes and durations, and monitor cost anomalies with auto kill switches if consumption deviates dramatically. A critical insight here is that defense must scale horizontally. Rate limits protect the model, while circuit breakers protect the platform. The YAML snippet shows how to configure token buckets and circuit breakers, turning strategy into actionable policy. Let's consolidate the lessons. First, strict enforcement. Apply hard ceilings at every hop: request size, token limits, recursion depth, and budget quotas. Second, trust verification. Treat LLM-generated content as untrusted. Validate outputs before passing them to downstream tools or databases. Third, graceful degradation. Systems should degrade rather than crash. Circuit breakers and load shedding maintain core services under attack. Remember that unbounded consumption poses both immediate financial risk and operational downtime. And in multi-agent or rack systems, even small inputs can trigger massive cascades of tokens and API calls. Security must address the multiplier effect, not just the initial prompt size. Keep these takeaways close as you audit your own systems. Defending against unbounded consumption isn't a one-time fix, it's a journey. In the first 30 days, establish a foundation. Set hard caps on max tokens, context windows, and recursion depth. Enable per-user rate limiting on all endpoints. Deploy dashboards to monitor token usage and latency, and define basic budget alerts for daily spend spikes. By 60 days, implement adaptive throttling based on system load, deploy circuit breakers for downstream tool failures, create egress allow lists for rack plugins, and set up query budgets with caching layers. By 90 days, focus on resilience and automation. Conduct chaos engineering and red team drills targeting exhaustion. Configure automated cost anomaly detection and alerts, implement automated load shedding, and define AI-specific service-level objectives tied to auto-rollback triggers. This phased roadmap turns theory into practice and ensures your defenses evolve with the threat landscape. Our journey doesn't end here. In episode 5, we tackle misinformation to phishing setup, showing how attackers fabricate credible-looking posts and announcements, then funnel victims through tailored landing pages and email chains toward credential theft. We'll also cover chain breaking, techniques to detect synthetic patterns, verify source authenticity, and stop redirection flows. If you found today's masterclass valuable, please subscribe, like, and comment. Your feedback helps us reach more users and shape future episodes. Don't miss the premiere. Turn on notifications so you're alerted when episode 5 drops. And remember to watch episode 3 if you haven't already. It explores how hackers bypass guardrails through system prompt leakage. Together, these episodes form a complete picture of the evolving threat landscape. Thanks for watching.